All right, let's get right into it. We'd like to think our view of the universe is, totally objective. But what if it isn't? What if our cosmic address, the fact that we live inside a galaxy, is introducing a tiny, hidden bias into our biggest measurements? Today, we're going to look at a really clever proposal for a cosmic checkup, a test to see if we're all weighing the universe on a slightly tilted scale. First things first, let's be super clear about what we're talking about here. This whole explainer is based on a note by Gerald Welch. And it's so important to get this up front. This is a diagnostic proposal. It is not a new cosmology. We're not talking about rewriting gravity or anything like that. This is all about putting our current methods and assumptions to a really tough test. So this is the big question, right? Could our very location be skewing how we see everything? I mean, think about it. We live in a pretty dense part of space. All our telescopes, all our data, everything we use to measure the cosmos is calibrated from right here in a crowded neighborhood. So, is it possible that's coloring our view of the whole universe? And that gets us to the heart of the problem, what the source calls an overdense anchor. It's a great term. It means we are fundamentally anchored to the crowded, galaxy-rich parts of the universe. Every single measurement we make is tied to data that comes from these kinds of places. Okay, so here's the core thesis. There could be this thing, a shared mode bias, hiding right in our best data. Why? Because all our different ways of measuring the universe, supernovae, galaxy clustering, the whole shebang, they're all calibrated using data from the same kind of dense environment. So if there was a tiny systematic error, it could affect all of them in a similar way. They'd all agree with each other, looking perfectly consistent, but they might all be just a little bit off from the true cosmic average. This is a fantastic analogy to make it all click. Imagine you have a weighing scale. To make sure it's accurate, you use a set of reference weights. But what if every single one of your reference weights was secretly 1 kilogram too heavy? Well, your scale would seem perfect. Everything you weigh would be consistent. You would have no idea there was a problem, not until you found a truly independent reference weight, one from outside your system, to check against. Now, to get specific about what we're actually testing, we need to define this key term, the baseline. Put simply, you can think of the baseline as our measurement of the emptiness of space, the effect of dark energy. Now, the proposal isn't saying that dark energy itself is different in different places, not at all. It's asking if our inference of it, our measurement, might come out slightly different depending on whether we're looking from a crowded spot or a really empty one. So, if our cosmic scale is potentially off, where in the universe could we possibly find that outside reference weight to check it? Well, the answer is just beautiful. We look to the emptiest places we know, the great cosmic voids. And why are voids so perfect for this job? Well, for one, they're enormous. They make up a huge fraction of the universe's volume. And while they don't have many galaxies, the tracers we usually look at, that's exactly what makes them so valuable. They're our cleanest look at the low-density universe, giving us a totally different environmental backdrop for our measurements. And this gets us to what void-anchored actually means. It's really important to get this right. It doesn't mean we toss out all our existing data and only use voids from now on. Nope. It means we run a controlled experiment. We use our existing data and methods, but we split the data based on environment. We run the numbers for the dense regions, and we run them for the voids. And then we compare them. Okay, that all sounds great in theory, but how do you actually do it? Well, the proposal lays out a very clear, concrete test using a technique called gravitational lensing, which is basically just measuring how the gravity of big stuff in the universe bends the light from galaxies far, far away. And here's the recipe, step by step. First, you grab a catalog of known cosmic voids. Easy enough. Second, you measure that lensing effect, the subtle stretching of background galaxy shapes around thousands of these voids, and you sort them by how empty they are. Third, for each bin of emptiness, you basically measure the strength of that lensing signal. And finally, here's the magic. You look for a trend. Does the signal strength change as the voids get emptier and emptier? And how does that compare to what you see around dense clusters of galaxies? Now, any really good scientific idea needs two things, right? It needs a very specific prediction that you can go out and test, and it needs a clear list of ways it could be proven wrong. And this diagnostic test, it has both, in spades. So here it is, the one big prediction that this whole thing hangs on. If the hypothesis is right, if measuring from dense regions is kind of watering down our results, then the measurements anchored in the voids should give a higher value for that cosmic baseline. And critically, that value should get steadily higher as you look at emptier and emptier voids. That's the key, a clear directional trend. And this is what makes the proposal so strong. There are so many ways for it to fail. If you run the test and find no trend with void depth, the hypothesis fails. If you find a trend but it goes in the wrong direction, it fails. If the results are messy or they change depending on how you find your voids, or if it turns out it's all just some known measurement error, the hypothesis fails. See? This isn't about just hoping for a result. It's a really strict, honest question you're asking the data. And the best part about all this, it's not some far-off futuristic idea. We can do this right now. The tools are already there. Cosmologists already have catalogs of voids. They already know how to do stacked lensing. The novelty here is just connecting the dots, using these existing tools to perform this specific, powerful diagnostic on our own assumptions. So, let's say we do all this work. What's the payoff? What do we actually learn? Well, this is where the idea is so incredibly powerful. Because no matter what the result is, it's a win for science. It's a true win-win diagnostic. Let's just walk through the two possible outcomes. Okay, outcome A, you run the test and you find nothing. No trend. That is an awesome result. It means our current methods are solid and we can actually put a hard number on how small any potential environmental bias must be. Now, outcome B, you find the predicted trend. Guess what? That is also an awesome result. It would mean we've discovered a real, measurable effect that we now have to figure out and build into our models. So at the end of the day, that's the real takeaway. This is what good science looks like. The test is designed purely for learning. You either gain a whole new level of confidence in the standard model of cosmology, or you uncover a fascinating new wrinkle that will make our understanding even better. Either way, we win. Our picture of the universe gets sharper. It really makes you wonder, doesn't it? For decades, we've learned about the universe by staring at the bright spots, the galaxies, the stars, the clusters. But maybe, just maybe, some of the deepest secrets and the most important checks on our knowledge are hiding out there in the vast, quiet darkness in between. What else is waiting for us in the empty spaces?